Okay, now how to do some of these with the calculator. So we have, we're going to use the position equation. So the height of an object at time t is moving in a vertical line with a constant acceleration a by the position equation s. So s is like the height at any time, 1/2 a. All right, so a is the acceleration. T squared is time squared, plus VO is the initial velocity times t, plus SO is the initial height. Alright, so we don't know any of that stuff. Alright, S is the height, T is measured in seconds, VO is initial velocity, SO is initial height. Alright, so we have to figure out what those acceleration, initial velocity, initial height are based off the 3 points that we're given. So you can like track a falling object with a sensor and see that, okay, at 1 second it's 52 feet high, at 2 seconds it's 52 feet high, and at 3 seconds it's 20 feet high. And just knowing those 3 points, you could find the model that represents the height of this. Alright, so we're going to set up a system on the calculator. So solve a system of linear equations. You could do equations too, but if you don't have a CAS, this will work. Alright, so we have 3 equations, and I'm going to make the variables, since we're looking for acceleration, initial velocity, and initial height, I'm going to make them AVS. Alright, so S, the height, is equal to 1/2, so I'll do 0.5 times A, which is what we're looking for, times T squared. Alright, now actually we do know what S is. So we don't know the initial height. So this S here, if we're looking at 1 second, right, based off this point that we're using, oops, tried to highlight that, but this point right here, the initial height is, for the height after 1 second is 52. Alright, so we got 1 squared, alright, plus the initial velocity, which we called V, fortunately you can't call it V sub 0, times 1, alright, and then plus S sub 0, the initial height is what we're looking for. Okay, then after 2 seconds, the height is 52, so we'll do 0.5 times A times 2 squared plus the initial velocity times 2 plus the initial height. And then at 3 seconds, the initial height is 20. So it's been like 0.5 times A, the acceleration, alright, times 3 squared after 3 seconds, alright, plus the initial velocity times 3 plus the initial height. Alright, and now we have our model. So what do these numbers mean? Well, that means if we make S sub t is our height over time, alright, I'm going to define that as 1/2, so I'll do 0.5 again, times negative 32, because that is A, because that's in the first part of this ordered triple. Alright, so negative 32 times t squared, so times t squared, plus the initial velocity, which VO we found to be 48, so plus 48 times time, times t, and then plus the initial height, 20. Alright, so this is now our model, so you can see, okay, after 1 second, the height was 52 degrees, after 2 seconds, 52 feet, sorry, after 2 seconds, the height was 52 feet, after 3 seconds, the height was 20, alright, and we can graph this and see what the height is over time. Alright, we could see what the height is after 4 seconds, alright, so using the intermediate value theorem, we see that the height had to be 0, so had to hit the ground somewhere between 3 and 4 seconds. Alright, if I do control add a page, alright, without losing that other page, I could keep S defined. Now, I don't know if this is going to graph because it's S of t. So if I wanted to graph, I would have to call it S of x. So let's fix that. So when you graph it on the x and y axis, it's not going to know to graph t. So now I could come here and graph S of x, and we see the height over time. Alright, and you can use that to answer different questions, like you want to find the max height, analyze graph, maximum, it's going to occur somewhere on this interval, All right, we see the maximum height of this object occurs at 1.5 seconds at 56 feet. If we wanted to see when it hit the ground, we would look for the 0, and we see that that happens at 3.375. If you wanted to get a better view, all right, you could do zoom box and just put this part in a box, and now we see a nice view of this graph.